Steve Camilleri, it's nice to finally meet you and welcome to AU Manufacturing Conversations.
Yeah, nice to meet you.
So the first question as always is, how did you get here and what do you make?
Right, so yeah, my name's Steve Camilleri, so I'm the CTO of SPEE3D. So we're a company that makes metal 3D printing technology. So we arrived at this business by a bit of a roundabout route. So the two co-founders, Byron and I, we are actually electrical engineers originally, specialising in electric vehicle technology. So that's a bit of a weird thing for people that are doing 3D printing now. We had a solar car that we used to race, and we had a world record for that solar car. I think we did a reasonably good job on that car. And one of the things that made that car competitive was an electric motor that was built into the wheel that we'd built from scratch. So there was a team up in Darwin, and we figured out this new technology for making high efficiency electric motor drives for electric vehicles. From the solar car, we decided that it would be a good idea to commercialise the motor technology. So it was kind of developed as part of a university project, which the solar car had been part of. So we started a company, it was called In Motion Technologies. That company was intended to commercialise this electric motor technology that we'd developed for the solar car. So we went on to work with a range of different companies around the world, adapting that technology for them. And in the end, we ended up deciding that we really needed to partner with a manufacturer. Manufacturing was a really important part of it. So we actually got bought out. That's what happens when you try and partner with a manufacturer. They bought us out. We ended up working with a company called Regal Beloit out in the US. Our technology turned out to be a good fit for a whole range of applications for them. So rather than teach their manufacturing guys how to work with our high-tech motor, they brought us in and decided to teach us how to do manufacturing so we could build the factories. So at this point, we're these wide-eyed university graduates and quite good in the academic sector and in research, and now we knew how to make factories. So that was a bit of an unusual thing, especially for an Australian. We built a range of factories around the world for this technology. That all went quite well. Some of the factories are still running today, many years later. We cornered the world's pool pump market, for example, which is a bit of a sad brag, but this...
The world needs pool pumps.
Exactly. And this motor used 80% less energy. So it was a huge reduction in carbon emissions, in energy and cost. And it was because we had this little miniaturized solar car motor inside of it. So in the course of doing all this manufacturing, we did a lot of metal casting. And what we worked out was metal casting, we were always doing it in small volumes, always doing it with a rush. And it just didn't work very well under those circumstances. So whenever we were prototyping and we'd order a metal 3D printed part, it would always come reliably within a couple of weeks, and it would always be right, which metal casting would never do, but it would cost like 25 grand. And we thought, if only there was some way of fixing the cost and improving the production speed of 3D printing, people would stop casting things because casting can be painful. So, there's a lot of varieties of casting. So we're just talking about the kind of casting we're doing in short campaigns and, trying to have a lot of variability in your process. No one would work with us. None of the 3D printing companies would work with us on trying to fix the 3D printing process to make it more manufacturing friendly. We got frustrated, we quit our jobs, we started SPEE3D. So we knew exactly what we needed. We had a technology-shaped hole. We had to be able to print parts very quickly, so we targeted 100 grams a minute as our metric. We also decided that the parts needed to be able to be manufactured cheaply, so we were targeting about $100 a kilo for our production cost. The first thing we worked out was that all the processes people were using already, namely using lasers and electron beams and things like that, could not possibly achieve it. So I had a page of physics that said speed limit by the side of the road, can't do anything about it. You're limited to about somewhere between 1 and 10 grams a minute. 10 if you go crazy and have lasers everywhere and huge amounts of expense, and 1 for kind of, just trying reasonably hard. So that was a bit of a sad day to finish that math and get to the conclusion that it was physically impossible. So.
But then you took a trip to Syro, right?
No.
Oh, maybe I've got the origin story wrong.
I think that's a Titomic thing. It's Titomic and Syro.
Okay, I thought I read an article by Alex Kingsbury ages ago that mentioned that you guys had to visit Syro.
Right.
Maybe I'm off the mark, but please, you're here to set the story straight.
So, we eventually did speak to Syro, but at this point, we've done the math, we've worked out we can't build as fast as we wanted. And so we tried to work out what the problem was. What's the problem? Why can't we print as fast as we want? And the limitation, in fact, was this thing called phase change. The idea that you have to spend time and energy to convert things from liquid to solid and then back from liquid to solid again. there's not much you can do about that. It's unavoidable. You've got to add energy to a substance to make it from solid to liquid and wait for the time for it to happen, and then you've got to do the reverse to turn back to a solid. So we thought, if only we could build the parts without changing the phase, without melting them at all. If we could keep it solid the whole time, the speed limit's off the table. That kind of was our aha moment, was working out that not melting the material was the solution to the speed limit. So we went out and had a look at all the different solid state processes that would allow you to fabricate metal, and we hit upon this thing called cold spray, which was developed in Russia in the 80s. Quite an interesting origin story to that all of its own. And we thought, wow, this is actually pretty close to what we think we need. So we looked into it a bit more, and there were papers at the time declaring loudly, this is a wonderful process, it'd be perfect for additive manufacturing, but you can't make geometries with it. It's too constraining. You can only coat parts with it. So, we love those kinds of challenges. So challenge accepted. There was quite a lot of mathematics involved, but we were able to crack the problem of how to use cold spray to make three-dimensional controllable shapes. There was a lot to it. At some point we worked out CSRI was indeed doing cold spray, so we went and had a chat to them. They hadn't cracked the problem either of how to make the three-dimensional shapes, so we knew we were on our own. But fortunately we had a network of good people from our history. We brought in all the right folks and we got our heads down, and it took us about a year, but we figured it out. So at that point we could take a 3D geometry, one that we'd never seen before, and we could figure out how to move a cold spray nozzle around to build that shape.
You started looking for something that could, I guess, maybe be somewhere near competitive with casting. There's problems that you're looking to address, as you've mentioned. You started not in defence, though. Tell me about, we're obviously here talking because we're at a defence event and you've just released a printer for that market. Tell me how you were drawn to defence.
To be perfectly frank, at first we weren't. I suspect we were going the same way as a lot of Aussie tech companies go, which is to say, wow, this defence thing is very big and complex and expensive. You can see giant behemoth companies and giant behemoth governments kind of battling it out to figure out the defence industry, and it was just terrifying. Yeah, anyone who has that impression, it's fairly accurate. We were very lucky in a way that the pandemic hit. So the pandemic came along, everyone was suddenly starting to have trouble with supply chain. So, defence included, their supply chains are built to be much more rugged and kind of rigorous than, for example, like, your local football club's supply chain. But, everyone's feeling the pinch. Things aren't moving as they were when the pandemic started. We met some people who'd won a competition internally within defence to look into metal 3D printing. We got along with them extremely well. They observed that we were already doing the kind of thing that they decided that they needed, and they couldn't find anyone else who could. So there was a bit of a coincidence that we were an Australian company and it was an Australian army people who had discovered this need. So that was all a bit suspicious for everyone. Why aren't the Germans or the Americans solving this problem better than the Australians? Eventually people got their heads around, no, it does indeed turn out that the Australian guys have what seems to be the best product. So we went forward and did some field trials. We did 3 of those. So, I'm just people can't see me on this, I'm a pasty engineer. I'm being dragged outfield into the dust and the heat to work alongside the army, and I got to say I really enjoyed it. It was fantastic. Understanding the way that these guys have to move and work, and the problems that they have during the day was just eye-opening for me, and mostly just to work out that the people that we were dealing with were very intelligent, very capable people who had very real problems that needed to be solved. Yep. Aside from the faceless organisation bit that most tech companies are worried about, the actual people are fantastic. So, we had some of our best experiences so far as a company working directly with army people, just very professional and dedicated, and with a really deep and clear understanding of what they needed to achieve. So, you don't often see this when you're talking to customers. You want all their customers to be extremely well informed about what they need to do, but it's not often the case. With army, it was the case. So we had a wonderful time working with them. We collaborated very strongly, figuring out the best ways to solve the problems and what was worthwhile, what wasn't worthwhile, where we should focus, where we should improve. And really through all that effort, we've come up with a new version of our product.
Right, well that's a good time to start talking about your new product. Tell me about how it's different from the warp speed printer, which I understand was a ruggedized version of which was used in the trials. Tell me about what it offers, how it's different to what you've done before, etc.
Yeah, sure. If we talk about humans and hierarchies of need, food, water, shelter. It turns out that people who need parts 3D printed have a hierarchy of need as well. If you can print something, what are you going to be yearning for? And if you can print something, usually you're printing with polymer, and you're going to be yearning for a better material. So that's the first thing that happens. Our process is about delivering normal kinds of material performance. The same thing people have been used to for the last 100 years. If you've got a nice cast or forged aluminium part, you want to be able to make the same kind of shape and get the same kind of performance out of the parts. The material properties have to be the same kind of performance. So polymer doesn't cut it there, unfortunately. We would be out of a job if polymer were strong, but it really isn't. It's also not good at high temperature. So metal's good at both of those things. Your first need is the material's got to be better. Okay, so now you can print, and now you can print out of good material. What's your next need? Well, your next need is you'd like to be able to make large parts. So by large parts, we mean the kind of thing that a human might have trouble carrying around, and larger. In fact, if you look around the world, there aren't really very many good processes around for making large parts. They typically take a long time, expensive tools, complexity. So 3D printing hopefully comes to the rescue here, right? Let's simplify the way that we do large parts. So we got into large parts. So we have had a printer out for some years now that'll do parts up to 45 kilos, a meter in diameter, which is well above what other people in the market do. Okay, now that we can do large parts, what's your next hierarchy of need? Your next one is you've got to be able to solve the problem, make the part where you have the problem. You don't really want to be exporting your need for a part all the way some distance through the supply chain to a place where there is a 3D printer and then back again. Every minute has value. So if you can move the printer to where you have the problem, then suddenly you're a new class of solution. Suddenly, the value just goes up exponentially. So our new printer is expeditionary. It can go where Army go. It can move as they do. Using their infrastructure, it can go by truck, by plane, by ship. It can indeed often be printing while it's moving. And the whole idea is to be able to take this manufacturing solution with you wherever you go. So what does that mean? Well, it really means that instead of being reliant on global supply chain with no better choice, now they've got a new option. And the new option is they can make their own parts when they need to.
Right, and it's out there in a shipping container looking very military and not like something that's in a factory, and fair enough. Could it be used by a company who wants to make metal parts on demand, or is it a different beast to the other printers you make?
It's an excellent question. So really, I think the market that we're looking at now is this kind of parts on demand market. So our new printer, which is designed to be expeditionary, our X-Speed printer, is really targeted towards people who have enormous infrastructure cost. So if you can imagine, if you had a mine or an oil and gas plant or a port or a farm, a huge farm, you're not the kind of person that yearns for a 3D printer, right? It's not something that's missing in your day. But what you do have is a lot of infrastructure, a lot of capital. And when that goes down very subtly and unpredictably, which, reality happens, right? When that goes down, you may not have any good choices on the table. You might be that infrastructure might be down for weeks or months, waiting for the global supply chain to catch up and get it going again. This deployable printer is your insurance policy. So that printer can be sitting there ready to go, and it could go, for example, out with the Army on deployment, but it could go out to a port for the busy time of year. It could go out to a farming community for the harvest season. Yep. And it will just sit there and wait for the things that go wrong. And then when they go wrong, suddenly you're back up and running again in a few hours and not a few weeks or months. So that's the real advantage for the expeditionary printer. Now, the same technology we also supply in a kind of a workshop setting. We have a thing we call the warp speed printer. Yep. And to be honest, the two printers have much the same level of capability in terms of what they'll print and the materials they'll use and so on. But the workshop printer is really designed to be static. So that's designed to be very low cost. So it's cheaper to get into, and the materials that it works with, it'll work very cheaply. So the main objective when you're manufacturing isn't so much being able to generate a part super quickly. The main thing you're chasing is I want to be able to deliver material of this minimum property, and I want to do that at the minimum possible cost. So manufacturing is all about competitiveness, and the competitiveness in that case is who can make parts of the right quality the cheapest. They win. Yep. So our warp speed printer is designed to help them.
Okay, and are you able to say anything about the cost? Is it a subscription or buy outright model, or what are you charging? How do we?
Yeah, it's complicated. We have a range of different options. Probably the easiest way to talk about it, we love to talk about this butcher shop method, so dollars per kilogram. So If we're talking about chuck steak, that might be $10 a kilo. If we're talking about Scotch fillet, that might be $40, $50 a kilo. People understand this butcher shop cost, right? Especially right now with what's going on with the supermarkets. We like to talk about our part cost in terms of dollars per kilo. So we wrap up the cost of the printer, the cost of the energy, the cost of the labor, the cost of the printing material, and we make that dollars per kilo figure. This is actually a process that we learned back when we were doing manufacturing years ago.
Yep.
So it's embedded cost, if you like. And we targeted about $100 a kilo, and in fact we've achieved that. So when you're printing and using the printer a little, it's usually about slightly more than $100 a kilo to make parts. When you're printing a lot, it can be a lot less than $100 a kilo. When you're talking about metal casting and the kind of campaigns that we would do, typically you're talking about $200 to $350 a kilo for that process, that 5,000-year-old traditional process, right. Metal casting. So what that means is this process is actually quite a lot cheaper than the best way you might otherwise get these parts.
And that's assuming you're just using aluminium powder, is that?
Yeah, that's right. The metal powders, we've found a range of ways to get those. I think in Australia, we'd be silly not to think about getting into sovereign capability for the powders. I mean, look at the value add. We're exporting alumina at $1 a kilo, and aluminium powder might be worth $80 a kilo. I mean, that's a lot of value add there. As a nation that's expert in generating these feedstocks, it'd be nice to go up that value chain a bit. So I'd love to talk to people about that if they want to talk about that. In the meantime, we're quite good at getting the material out of Europe, the US, the UK, Asia.
Yep.
So there's plenty of sources of it around. And I think there's just going to be more and more metal powders in the future.
In your release today, it says MTC is the first development partner. Obviously, you've spent time, as you've just mentioned, developing this with the Army. Why is your development partner an overseas organisation? I mean, it's up to you where you get stuff done, but I'm just curious.
Yeah, I think it's quite important when you're working with new technology. So let's be frank, our technology is a disruptive technology. We're changing the way that we think people should operate. And we think we've got the justification for that, and indeed a lot of people agree. But that's fundamentally what we're asking people to do, is change the way they operate. So disruptive technologies ask this of the customer. We're here in Australia, we're very distant from a lot of the world's markets. What we really need to do is find people we can work with in every region that people in that region trust. Because ultimately I'm a salesperson, it's my job to get technology into people's hands. I think on the face of it, I do a pretty good job at stepping aside from that and trying to help people to find the right answer. But ultimately, I'm viewed as a salesman. So if we can find partners in those different regions where we're seeing good applications for the technology, then those customers who are working with us have someone they trust that they can work with, who's not us in our biased form. And if they have problems, we would help them. But ultimately, they can go to the people they trust in their own region to help them. So this is why it's really important for us to find people like MTC that we can work with to mark our homework, to make sure that things are done properly in that region, and the customers in that region can then trust them.
Sure. And so speaking of international work, REPTX, I'd like to know a little bit more about that. I read recently that you print off some big bronze anchors and other parts. Tell me about that exercise, what was done and what you learned from it.
Yeah, so REPTX was really interesting. So this was an exercise run by the US Navy. We were located in a port off LA, Port Wainami it's called. The point of the exercise was to demonstrate radical new maintenance technologies. So, maintenance technologies don't normally go together, those two words. But 3D printing really, if you ask me, one of its best applications is a maintenance technology. So if you've already really got a good way of making parts, why would you go to 3D printing, right? But if you've got a really interesting way to maintain your infrastructure with 3D printing, that's a totally new angle for 3D printing, which we think is incredibly valuable. So REPTX was about testing us in that capacity. So we brought our printing technology there. The idea was that we would be trialed for a few different case studies. They were going to test us out on a few different things they'd thought up. We had most of those covered on the first day. So we were sitting at the port facility at Port Wainami with our 3D printing capability. Our job was to make these case studies. However, we're surrounded by other companies who are also trying to do interesting things and demonstrate to the Navy. And of course, we had the Navy's Defence Test Ship, which is the ship that's made available to test new technologies. That was part of the exercise. Suddenly, there are all these people coming to us constantly. Can you do this? Can you do that? What about this? What about that? So the Navy's case studies were fairly rapidly dispatched. Suddenly we were helping every other company there and all the people who worked on the self-defense ship. So we were making, parts for the seals on their doors. We were making special covers for protecting parts of the ship. We were helping with some corrosion issues. And we were doing all of this from our little tent there at the port. So what we discovered during REPTX was that people actually didn't particularly understand what our technology could do yet. So I think our marketing's been very, very good. But in a typical Australian fashion, we have kind of failed to completely describe what the technology does. We've kind of done our tall poppy thing and avoided talking about ourselves too strongly. So what does our technology mean? What it means is your problems go away. So you can be a port facility, you can have problems with supply chain, you can have problems with reliability, with maintenance. All those problems go away with the technology. So REPTX really afforded us this ability to demonstrate what our technology did right there at the coalface and prove that it would solve the kinds of problems that people had. So having done all that, we were invited to put our printer on the ship and test it on the ship. So people do worry about 3D printing on ships. Most 3D printing processes use a powder bed, and powder bed needs things to be level, and ships aren't level. And maybe they're level for moments, very occasionally, but they're typically not level. So our process doesn't have a powder bed. So we'd always thought it would print quite well on a ship. So we're shooting our material into our part at several times the speed of sound. So we'd always thought that the small motions that were involved, the very low speed motions involved, probably wouldn't affect us very much. So of course, nobody believed us. I didn't believe it a little bit myself, but now we've been on a ship. The ship was rocking and rolling and it was making parts. And we made a series of parts all the same, these little anchors. We thought, let's be classy, let's make something that's interesting and themed. So we made these little anchors over and over again, made a range of them. They're all off being scanned now, and we're writing a research paper about how little variability we see printing at sea state on a ship.
Been a while since you've written a research paper, I'm guessing?
I do write them occasionally.
Yeah.
To be honest, I'd like to be able to give back more than I do, but the time constraints are a problem. Yeah, it doesn't especially do anything for us as a company, I think, to write papers, but I think it's important to do all the same.
Yeah, well, I'm guessing you're a pasty-faced engineer who values knowledge development. It must be a fulfilling thing to do.
Yeah, that's right. And I mean, if we don't write down what we learn, then some poor person in the future is doomed to make our mistakes all over again.
You mentioned anchors. Let's talk about a different kind of anchor. You're one of your, inspirations, or a company that you're borrowing some approaches from. Tell me about ANCA, why you've chosen to emulate this much respected Australian machine tool company, and what it's involved and why they're worth borrowing from.
Yeah, excellent question. It's interesting to look back at Australian success stories and try to boil down and understand why they've been successful. So, as I mentioned already, our isolation can be a problem. I think it's also one of our advantages. So we have this willingness to do something different here, this need to invent, because quite often we don't have good support. The support might be on a completely different time zone. So we have to solve our own problems. So this is just like a farmer. A farmer's out in the field, he's got a problem, he's got to solve it himself with, chewing gum, rubber bands, whatever it might be. Really, that's our national culture. It's something like that, because we're out here on our own. We don't have healthy supply chains to neighbouring countries and huge populations that we can draw on to help us solve our problems. We're here kind of on our own. That gives us a bit of a reverence, I think. I think that's an essential part of the mix as well. A bit of arrogance, maybe, we think we might be able to 3D print parts better than Toyota. I guess in some parts of the world you wouldn't be able to think that, but here in Australia we're quite happy to do it, wrong though we might be most of the time. So I think that's a healthy mix in terms of us being able to solve problems in a way that's a bit unusual and maybe, I would judge at least, a bit more effective than in other places. So the downside is the isolation.
Yep. Once
we've solved the problem, we're very, very far from everywhere else. So our domestic market here, it's about the same size as Florida for the whole country. So, that's not a big market. So what do we do? How do we solve this problem? And you look back at different companies, ANCA included, and you try and look at how they've solved that problem. And really, it's just by continuing to do what they've done to solve their technical problems. So you find good people to work with overseas, you set up distributorships, you set up support, you regularly cycle your people through. ANCA was one of the closest in terms of where we'd like to be eventually. So I think it made a lot of sense. I mean, they're a Melbourne company, we do our manufacturing in Melbourne, we know a lot of the same kind of people.
Yep.
And we were able to benefit from some of the lessons that ANCA had already learned by talking to those people who'd learned those things at ANCA. So, they make CNC machines, grinding equipment. Essentially, they make tools that make tools.
Yep.
That's what they do. We don't do that, but we're still relying on heavily automated large pieces of equipment that we'd very much like to sell to other parts of the world. So that that description suits us and ANCA. So what had they done that was successful? And it's just hard work. They'd done the hard yards. They'd set things up. They'd flown to places, worked with people. So we've just got into it, head and shoulders straight into it. Exactly the same kind of approach. Like, let's go to the world.
Yep.
And let's make sure we succeed, because we know that our domestic market isn't enough to sustain us. It's just the curse of being Australian. The curse and the benefit of being Australian is this isolation. So we thought ANCA managed that extremely well.
In my ignorant opinion, I'd see similarities in terms of you being, sort of engineer-led companies that have a deep understanding of a customer problem and who will work with a customer and can bring a lot of value, and also a strong, really, really strong focus on software from way back. So my 5 cents is I see that similarity set between you two for whatever it's worth.
Yeah, I think that's completely fair. I guess we've both been early to recognise that in our chosen industry, automation was the key.
Yep.
Yeah.
Yeah, very good.
Maybe another uniquely Australian insight.
We're allowed to have them.
Yeah, that's right.
Defence is becoming or has become your biggest market for your machines?
I'd say it's probably 50-50, defence and other at the
Yep.
moment. Defence has certainly grown more than we expected it to. And, I think, to be honest, luck has played a big part in this.
Yeah, you're mentioning.
Like we've come into existence and demonstrated that we can do what we can do, open Pandora's box at about the time in history when it turns out global supply chains are a huge mess, all snarled up by pandemics and, conflicts and the rest. It's just been fantastically good timing. I mean, it has to happen sometimes, right? You can't have poor timing all the time. Occasionally timing has to work in your favour. And I think it has for us. We've been extremely lucky. Defence has paid more attention to us than I guess they would have if the world hadn't been such a mess. And so that's worked out for us very well.
Right. And how do you see cold spray additive manufacturing changing the way that defence does maintenance? And how do you see it playing a bigger role in defence? What are your sort of, trends you can outline, and where do you see things going?
Yeah, right. So I'm going to give you an answer to this you're not expecting, probably. So I like to try and understand the philosophy of things. In this case, it's how does defence supply themselves? How do they sustain themselves? How do militaries work? So I guess if I'd ever been in the military, which I haven't, I probably would have had a bit of understanding, but I didn't. So I was quite curious. I went out and did some research. One of my favourite books that I unearthed was the Civil War Ordnance Manual from, back in the day in the US. This manual talked about, had whole chapters on how to mine hills and take resources from native forests to build cannon in the field. What an exotic idea is that, right? I mean, we never think that way anymore. You turn up with literally nothing and you've got to figure out how to make normal defence things. Like, imagine building a Bushmaster or an M1 main battle tank the same way. Like, you just couldn't do it, right? But at some point, that was how it worked. There are Roman forts in Brittany, from Brittany, from the UK, where they had to abandon the fort, and so they deeply buried in their well their entire supply of iron nails. Why did they do that? Because that was military technology at the time. So defence have always made their own stuff up until recently, whether that's horseshoes or bows and arrows or armour. Defence industry has always existed, and defence has always worked with them to supply themselves. So the global supply chain, if you ask me, has been a little bit of a short-term aberration. So really over the last kind of 50, 80 years, defense around the world has turned to a global supply chain because of efficiency. What they haven't really explored in particular is the strength of that supply chain. And when things have gotten shaken up as they haven't been as strong as people had hoped. Here's the interesting thing about additive manufacturing, advanced manufacturing as it's emerging, is the moment that the global supply chain's efficiency can be done, that same level of efficiency can be achieved by you where you are as a defense force, you just switch back, I think. Once you're at a point where you can do the same thing that you would do on the other side of the planet in massive volume, and you can do it in ones and twos as you need them where you are, like why would you ever go back? I'm hoping, one of the things that I think will be an outcome here is a massive decarbonisation, because suddenly we won't be moving things nearly as much as we have in the past, because we won't need to. We'll be able to make things much, much closer to where we need them. And we did some tracing with some groups we were working with on spare parts. And we looked at how many times those spare parts had moved by air, one part, how many times it had moved by sea, how long it had been in warehouses. The numbers were crazy. This idea that you make something efficiently on the other side of the world, you transport it once, you stick it in a warehouse, and a few weeks later it gets employed, that's not how it works. There's incredible amounts of inefficiency in that system, incredible amounts of waste, which doesn't just work in terms of dollars, it works in terms of carbon as well. Yeah. The idea that you can have this generalized feedstock that will solve a variety of problems and then solve the problem right there where you have it, it's incredibly efficient. Yeah. It's very close to what defense forces were doing 100 years ago, and so I think it'll be a natural progression to go back that way. Inevitably there'll be complexity and OEMs and technology and IP management, all of that will exist as well. That'll be a template on top of all this. But the broad movement is towards closer to the point of use. Yeah. I'd hate to be the guy right now who owned a massive factory in Atlantis that made hose fittings, because at some point soon nobody's going to be buying them. They're going to be making them themselves right when they need them. Our technology will already do that. We've spoken for quite a while, and I should probably let you go. Lastly, is there anything you want to plug? Perhaps you want to say a little more about the new machine, or floor's all yours? Right. So I'd like to talk about Australian industry development. So I think we're at a very interesting time in history here in Australia in particular. My whole engineering career, I've really watched Australian manufacturing struggle and founder, and I found that very, very depressing. As we were building our motors, it was all overseas work, despite us trying very hard for it to be otherwise. And really, we've been outcompeted by those countries who have, very low labour costs, very low cost of compliance with safety systems, environmental systems. We've always tried to do those things to a gold standard, and we should do. But it's meant that we've found it difficult to compete with other nations that aren't up to the same standard. So I think there's two inputs to manufacturing cost. So one of them is your materials cost, and one of them is your conversion cost. And in the past, we've always had fantastic materials cost. Like whatever the world needs, we've got the dirt you can get it from here in Australia. And we've got it cheap. We're excellent at extracting it at low cost. World class. This is why we're such a big exporter of minerals. It's not because it's cheap to extract, it's because we're good at extracting it. It's innovation that's driving that. Now, the other part of the cost is the process cost, converting it from the raw materials to the thing that people actually want to buy. We've always had trouble with that. Not all the time, but I think we have a real problem with our confidence level, especially coming off the back of the automotive industry, with our ability to process material and generate good quality products at low cost. And we've seen that people overseas have done it better. Advanced manufacturing solves this problem. Suddenly it's all about design, it's all about customer service, it's all about marketing and branding, it's all about coming out with the best product, and it's not about having this giant facility full of extremely low cost people. We've never been good at that. And to be honest, I don't think we want to be good at that. We want to be good at the design, we want to be good at the product. Additive manufacturing brings it to the table. So I think it's our time. Steve, thanks very much for being on AU Manufacturing Conversations. It was great to speak to you. Yeah, no worries. Thanks very much.